All right, it's 8:30. Let's go and get started. Good morning, everybody. How's everyone doing on this very wet Tuesday morning? It's raining like crazy out there. It could be an hour and a half to get here this morning. I thought it would be. I made it here. And we're going. Okay, so the plan for today, hopefully we can finish up our lecture notes on integral vector calculus. And so after today, you should be able to do everything on the homework. I think you should be able to do most of what's on the homework so far. I think maybe for the last two problems. But after today, you should be able to do everything. So announcements, remember homework 4 is due this Sunday. And so, that should be the last thing before spring break. And so make sure you guys turn it in. And we have the mid-semester check-in as well. And so there's a survey that I posted on Canvas. And so make sure you do that as well, because that is worth about half a homework assignment's worth of points. And so it can only help you guys. And so please fill that out. But it does count as another assignment. So it's not extra credit. So, please make sure you do it before the deadline is. Okay. All right. And so that is all my notes. So are there any questions I can answer before we get started? All right, so let's pick up where we left off. And so on Thursday last week, we were talking about Green's theorem. Let's go ahead and pick up. And so Green's theorem, remember, is one of the two main theorems of integral vector calculus that we're talking about in this class. And remember what I mentioned last week, that when we're going over these things, we're basically doing a not even like a tour or a review really of vector calculus, right? We're doing this a very quick drive-by, right? So we're basically just driving on a freeway, we're seeing vector calculus, we're saying hi to it, and then we're moving on. Okay? And so we're not really going to get into too many of the details of how to actually complete these things. What I really want you guys to get out of this section is what is the, when you look at theorems like this, when you look at equations in vector calculus, I want you guys to have kind of a physical intuition in terms of what these equations are representing, okay? And so that's what I want to start with today. So we're going to start with Green's theorem, we're going to talk about its physical interpretation, and then we're going to move on to divergence theorem in the second half of the class. Okay. Because again, you're going to see theorems like these, or your future classes are going to use these theorems to represent, certain physical phenomena if they haven't already. Green's theorem in particular is used in fluid mechanics, and so if you've already taken that, then you might have already seen this interpretation. But if not, if you're taking fluids next year, then this will be particularly relevant. Okay. So the mathematical form of Green's theorem looks like this. And so it's an equivalency statement between a line integral and a double integral. And so what Green's theorem basically states is that if we have a line integral of a vector field F, okay, and so this here is a line integral around a closed path. Of a vector field path. Okay, so remember last Thursday we talked a lot about line integrals and how to compute those. What Green's theorem says is this is equal to a double integral over a region R of the curl of the vector F, same vector field F. So this is a double integral. And what Green's theorem states is that these two quantities are equivalent. Okay. And so the key to this equivalency here is that, when we have our closed path of the line integral, which I'm going to call C, okay? And so that C is a closed path in a vector field, and the region R, those two are referring to the same area in space, okay? And so visually, it looks like this. So, let's say we have a vector field. So this is going to be the vector field F. These are different color for it. Vector field F, remember, is just the field of arrows. Okay. Okay. Right, so remember, vector fields are nothing more than just a field of vectors, right? And so it's basically a bunch of vectors defined at different points in space. Okay. And so what Green's theorem says is if we define a region R, and so it can be fairly arbitrary. It doesn't have to really mean anything, or it doesn't have to have a specific shape. Is what I mean. And so if we define a region R, so if I kind of just draw a globular region like this. And so this region here is the region R. Okay. Remember, whenever you take a 2D integral or double integral, you're doing it over a region in space, right? And so that's the region of space that we're taking our double integral on. And then what Green's theorem basically says that if we take a path around the same region R, and so in purple here, in purple there, I've drawn a path around. Okay. And we're going to call that path around C. Okay. And so as long as we're talking about the same region in space, where on one side for the line integral, we're talking about the path around that region. Okay. And for the double integral, we're integrating over the entire area of that region. Okay. As long as you have the same vector field F, and you take, on the one side you take the line integral, on the other side you take the curl, then those two quantities are going to be the same. Okay. Right. And so this visual is important. And so this visual is kind of key to kind of understanding the the equation. So the equation is important, of course. That's what you compute, but the visual is kind of how you kind of physically see it. Okay. All right, so that's just the statement of Green's theorem, and that's kind of how you kind of visually represent. Next, we're going to talk about how do we actually interpret this. And so what does the line integral represent, and what does the double integral actually physically represent? And I'm going to use the analogy of fluid mechanics just because that's kind of the most natural thing. And so if you've taken fluid mechanics, it'll probably be a little bit easier to understand. But if you haven't taken fluid mechanics, it's okay. I'm going to do my best to kind of explain it from assuming that you haven't taken fluid mechanics. But before I do that, are there any questions on? Okay, so let's talk about the physical interpretation. And I'm going to go on both sides. And so, you know, I'm going to tell you kind of what, let's talk about what the line integral represents physically, and then we'll talk about what the double integral represents physically as well. Okay, we'll start with the line integral. So this is the first half of Green's theorem, so it's the left-hand side, okay? And the key thing here is I want you to look at the integrand. So let's look at kind of the dot product in the integrand. Okay? We have two terms here. On the one hand, we have f vector. Okay, so remember this is the vector field. Raining so much I forgot how to spell. Right? And then what we're taking the integral of is the dot product between the vector field and dr. Okay? Remember what dr represents. Dr right here is the tangent. That's the tangent to our integral path, right? So remember when we're taking a line integral, we're taking it around a path, right? And so dr represents the tangent of that path. Okay. And I keep forgetting this, but you know, the name for the path, we'll call that C. Okay. So these are two separate things. So we have the vector field which exists on its own. Usually that vector field represents a velocity field. And so if you have some fluid that's flowing in a certain region, the velocity field represents, you know, the direction and the magnitude of which, you know, the flow is going. Okay. And then we have dr, which is the path that we're actually integrating on, which is kind of its own separate thing. Okay. When we take the dot product between these two quantities, what we're basically looking at is how much are the vector field and our integration path, how much do they align? So let me show you kind of what I mean by that. And so when I say a line, right? If we have the vector, if we have the path, I'm going to use, I'll use purple for the path. Okay. Opposite way. Okay. Right, we walk around the path in one direction. Okay. That's the path C. Let me go ahead and draw the vector field. So let's say that we have a vector field that kind of goes in just kind of one direction. Okay. And so let's look at this region right here. All right, and so in this region, you can see that our path in purple and our vector field in red, you know, they're pointing in the same direction, right? And so in here, we can say that the two, F and the path, are well aligned. And so when we take the line integral around that part, you know, we're going to get something pretty large because they're well aligned. On the other hand, let's look at this one. Okay. It's not drawn very well, but what I was intending was that, you know, the vector field F and the path C, they're perpendicular to each other, okay? And so in this case, they're not. And remember when we talked about dot products a couple of weeks ago, right? When you have two vectors and they're perpendicular to each other, and you take their dot product, you get 0, right? Because the angle between them is 90 degrees. Okay. All right. And so what the line integral is going to do is that it's going to compute these dot products all the way around the path, and then basically add up all of their contributions. Okay. And kind of the key to this whole interpretation is the fact that our integration path here is not an open path. We go in a circle, right? So, you know, eventually we're starting and ending at the same time. And so, you know, if we take that kind of as you know, kind of the key part, what this line integral is saying is how much the vector field F kind of goes in a circle, right? That's what the line integral represents. Well, the line integral is, remember, it's computing because of the dot product, how well F and the path are well aligned. But because the path is a circle, okay, that means our integral here is going to represent how much the vector field F also kind of goes around in a circle. And so in fluid mechanics, this kind of happens, or the most, I would say the most, you know, representative, you know, situation where this happens is when you have a whirlpool, right? And so when you have a whirlpool, you know, let's say that, you know, you fill up your sink and, you know, you keep the plug plugged and you pull it, right? What's going to happen is that the water is going to swirl around in a circle, right? And so in that case, you know, the velocity field also kind of goes around in a circle, okay? And so what you're going to get from that, if you take the line integral of that vector field of your sink, of your sink field kind of going around in a circle, you're going to get something significant. Okay. And so in fluid mechanics, you know, this quantity, this line integral specifically, it represents something called circulation. Okay. Circulation being the tendency for a fluid velocity field to kind of rotate in a circle and within a particular region. Okay, so that's how we physically kind of interpret the line integral. Okay? That one is a little bit of a lengthy explanation just because, you know, line integrals, I'd say are not, the line integrals aren't super common. And so, you know, that's why I kind of took a bit more time to kind of explain that. The double integral is a little bit easier to explain, especially now that we have this idea of circulation kind of on our. But before I get to the double integral, are there any questions on the line integral side of things? Okay, so let's look at the double integral part. So the double integral over region R the curl vector field dx d. Okay. And so I'd say the most significant part of this integral here, again, is the integrand. And so what exactly we're integrating. Okay? And so in the integrand here, we have the curl of the vector field F, right? So we talked about curl about a week ago. Okay? And what the curl represents is something kind of similar, right? And so the curl here represents locally in kind of a very small point, how much the vector field F tends to rotate at that particular point. Okay. It's a little bit different than the line integral because the line integral, that's over an entire region, right? When you take the curl just by itself, and so just ignoring the double integral, the curl represents that if you're standing at one particular spot, right, and you just don't move, right, the curl represents how much the vector field is kind of swirling around you, kind of a small region. Okay. Right. So for the double integral, what we're doing is we're computing the curl everywhere in the region R, and by performing the integral, we're adding up or we're summing up all the little curls over an entire region. And so if you sum up all of the little curls in a region R, okay, what you're going to get is basically an expression of the total amount of curl or the total amount of rotation in that region. And this idea of the total rotation, and so the total amount of rotation in a particular region, has a name. And so that name, we just went over it, is the circulation. So this exactly is the same thing as the circulation. So in other words, Green's theorem, we may as well rename it as the circulation theorem because both sides of Green's theorem are just a different representation of how to represent this idea of circulation. And so, I'd say the most kind of physical example or the kind of most classical example of this is in fluid mechanics. And so if you're taking fluids, maybe this is something you've seen. I don't think every fluid mechanics instructor goes over circulation, but it is a very core concept in fluids. And so if you plan on taking more advanced classes in fluid mechanics, like I know next year we have an aerodynamics class. I think it's happening right now, actually. And so this is definitely something that you'll go over. So it's a concept for that. All right, any questions on this? Okay, all right, so that's Green's theorem. And so now that we're done with Green's theorem, let's go ahead and move on to 3 dimensions. And we're going to talk about triple integrals, but more importantly, surfaces and surface integrals. Okay. All right, so we're moving on up. So, we've done everything. Green's theorem is primarily a 2-dimensional integral theorem. Now we're moving up to 3 dimensions. Okay. And so we're going to start our discussion with surface integrals. Okay. And so it's similar in concept to the line integral. And so, one way that we can interpret the line integral is that it's kind of a generalization of just a regular old 1D integral. Right? And so a surface integral can be thought of as a generalization of a 2D, a double integral. Okay. So normally for a double integral, we just went over one. Right? Usually we take it over some region R. And I'm using a square in this case. Okay. So usually when we talk about double integrals, we're usually talking about 2-dimensional space, and we're integrating over that 2D space. Okay. Now, for a surface integral, we're still integrating over a 2D surface. So it's still on a flat, surface, except now that flat surface can exist in 3 dimensions. So it can kind of have curves to it, it can kind of bend, and so on and so forth. Okay. So this is the surface integral. I will say that this becomes a lot more difficult to draw because it's a 3-dimensional object and I have a 2-dimensional iPad, and all the artistic talent in my family went to my sister. She's a dancer, she's an artist. I am the engineer. So I'm not very good at drawing, but I'll try my best. Okay. And so imagine this is a kind of a curved curved surface, almost like think of the surface of a sports car. Okay. And so it's still a 2-dimensional object, right? And so it's still, imagine it's like a sheet of paper, okay? Except now that sheet of paper can bend in 3D space, kind of like this. Okay. And so we're integrating over that surface, but that surface is 3 dimensions. Okay. And so just like we did for line integrals, our first step here is to talk about how we're going to define the surface, how we're going to parameterize these surfaces. Okay. And so for line integrals and for paths, we had just one parameter, right? And so we had one parameter because there's a 1-dimensional object, right? That 1-dimensional object could go through 2D or 3D space, but we only needed one parameter, one variable to describe it. For a surface, because it's essentially a 2-dimensional object, we need 2 parameters or 2 variables to define it. And the variables that I will typically use are U and V. And so what we say is that a surface is defined as R of U and V, where R of U and V to X of U and V, Y of U and V, Z. You can think of U and V as kind of like the generalized coordinates along that surface. Okay, so for certain values of U and V, it's going to this function here is going to tell you what your coordinates are going to be on that surface. And so again, this becomes a lot more difficult to visualize. So let me give you a couple of very common examples of parametrized surfaces. Okay, so let's do an example of a cylinder. Okay. And so I'm not talking about kind of the interior of the cylinder. I'm just literally talking about just the outside of the cylinder. Okay. And so if we talk about the outer shell of a cylinder, okay, this has an XY representation of x squared plus y squared is equal to a squared. Okay. And in the z direction, we go from -1, let's say, to 1. Okay. Okay. So the parameterized representation for this, in terms of UV coordinates, is the following. And so R of U and V, the cylinder, is equal to A cosine of U, A sine of U, and so that's how we represent the surface of a cylinder using UV coordinates, right? So we only need two variables here for the outer surface of the cylinder. Okay. So this A cosine U, if we relate this up to our equation up there, this A cosine U here will be X, U and V. This A sine U will be Y of U, V, V. And technically the Z is only a function of V, and I guess the X and Y are only functions of U, but that's how you match it up to the equation. And remember, this only represents the outer shell of that cylinder. And so you can plug in various, coordinates or various, examples of U and V, and no matter what you plug into there, it's going to land you on the outside of that. Okay. All right, any questions on this? Okay, let's do one more example. Another very common example of a parametrized surface, the outer surface of a sphere. And so normally in XYZ coordinates, a sphere is given by x squared plus y squared plus z squared is equal to a squared. Oh, which I should have mentioned above. So a here is the radius of the sphere. Okay. All right. So the parameterized representation . This one's a little bit more complicated. Here's the following. So we have A sine of E sine U, A cosine of V sine of U, A sine. Okay. And so you plug in different values of u and v. And so obviously, what we're using here is spherical coordinates. And so u and v usually is going to be some value between 0 and 2 pi. But if you plug in for that, then that of any value of u and v into that expression there, it's going to land you somewhere on the surface of that sphere. Okay. Right. So those are two examples, and so we'll use these examples in other examples later, especially the sphere. But these are examples of basically surfaces that exist in three-dimensional space, but we're just talking about just the outer surface. Okay? And so the analogy that I always like to think about when I'm thinking of just surfaces in 3 dimensions is think of like wrapping paper. Right? And so if you have a 3-dimensional object, if you wrap it in wrapping paper, the wrapping paper there represents kind of the the surface that we're talking about. Okay, any questions on this? Okay, all right. So now that we know how to represent surfaces and we know how to parameterize them, let's talk about tangent planes to a surface. And normal planes. Yeah. All right. So once again here, I'm going to draw an analogy to what we did for parameterized curves, right? Remember when we talked about parameterized curves and eventually the line integrals, one thing that was important was to compute the tangent vector to a curve. Okay. For surfaces, what we're interested in is the tangent plane, right? But the way that we find the tangent plane is going to be very similar to how we computed the tangent vector for a curve. What we did for line integrals was we just simply took the derivative of our parameterized curve. Right? So for surfaces, we're going to do the same thing. Okay. And so to find the tangent plane, what we're going to do is we're going to take the derivative of our parameterized surface. First, we have two variables. And so we're going to need to take both derivatives. Okay. So we have partial r, partial u. This is equal to partial x, partial u, partial y, partial u, and partial z, partial u. Okay. And we have partial r, partial v. Okay. This is partial x, partial v, partial y, v, z, partial v. Okay. And so if we take these two derivatives, we essentially get two vectors, right? So these two derivative expressions are vectors. Okay? And what's unique about these two vectors and what they have in common is that they're both tangent to our surface. Okay? They're going to be tangent to our surface at a given value of u and v. Okay. All right. So I'm going to do my best to draw this again, but maybe not be so successful. So let me use a sphere as an example. And so let's say that a particular value for u and v will put us on this location for the sphere. Okay. I'm going to draw kind of a dot right there. So this is going to be for a fixed u and okay. All right, so we have our spherical surface. So imagine like a basketball or a soccer ball or something, okay? And then imagine you're taking like a piece of paper and you're putting it, and you're kind of holding it flat and you're putting it right on top of the basketball at that point, okay? And so what we're gonna have here, plane. This plane is gonna be tangent, or it's gonna be sitting kind of right on top of our sphere at that point. Okay. So the two derivatives that we just computed, that partial r partial u and partial r partial v, right? What these two vectors have in common is that they're both going to exist in this plane, right? And so if I were to draw, maybe this vector right here, red, partial u, partial r partial u. Okay. And this vector, they may not be perpendicular to each other. Partial r, partial v. Okay. And so they're both within that kind of tangent plane that originates from that point u and. Okay. So the way I kind of drew it here, we kind of did it in reverse. And so, the way I did it here was I drew my surface and I drew the tangent, and then the vectors went into that tangent plane, right? Usually it goes in the reverse way. So the first thing you actually compute are the two vectors. And when you have two vectors in 3D space, those two combined can form a plane, right? And so that's kind of how you kind of define the tangent. So the tangent plane is thus defined by these two tangent vectors. Okay. Any questions on this concept here? Okay. Right. So that's the tangent plane. Okay. We also need to talk about the normal vector. Okay. Because whenever you have a plane, you can have a vector that's normal to the plane. So it's basically a vector that points directly away from the plane. And a lot of times, when you're talking about three-dimensional space, and you're talking about kind of arbitrary surfaces in space, a lot of times the normal vector is something that's actually more useful, because then that kind of tells you, which kind of how to point away from your surface. So this is something that's going to be important, especially once we get to divergence theorem. I'm going to draw kind of a visual representation from a sphere. It's like a form. Okay. And so if we have a sphere, you know, and we have a fixed point here, U and V. Okay. A normal vector would point directly away, such that, you know, if you were to compute the angle between this normal vector and the surface, you get a 90-degree. Okay. So it points kind of directly away. So the normal vector is an important concept. So, you know, later on today, we're going to talk about the divergence theorem. And the divergence theorem has to do with this idea of flux, right? And so flux is basically telling you how much a certain quantity is passing through your surface, right? And so we're interested in seeing, how much is going to pass through. And so to compute that, we need to know, how to basically quantify the direction that goes through the surface, which is by the normal. Right. So to compute the normal vector, we actually utilize our two derivatives up here. Okay. And so to compute the normal vector, what we do is we take our two tangent vectors, which are the two vectors that we had above, and we take their cross product, right? Because we know that when we take the cross product of two vectors, our resulting vector from that is going to be perpendicular to the two vectors that we put in. And we know that our two tangent vectors are going to be tangent to the surface at that point, right? And so we kind of utilize all that information. Normal vector, normally we give it the symbol n hat, okay, is equal to partial r, partial u, cross product, partial r. Okay. And then usually what you do, this is pretty standard. So normally when you compute this normal vector like this, it's not going to be normalized. And so its magnitude is not going to be 1. And so typically what you do after this is that you divide this vector by its magnitude to make sure it has a magnitude. You get a unit normal vector. Any questions on this before we do a quick example? Okay, all right, so let's do an example. I'm going to use a sphere again. So let's compute the tangent vector, or excuse me, the tangent plane and the normal vector to a sphere. Okay. Okay. And so a sphere, let me go ahead and write down its parameterized form again. And for a sphere, we have R v v is equal to A cosine of B cosine U, and then A cosine E sine u, then A sine. Where A here, remember A represents the radius of that sphere. Okay. Okay. So let's go ahead and compute the tangent plane. And so the tangent plane, remember, we are going to compute our two derivatives here. We have partial r, partial u, and partial r, partial. Okay. So let's go ahead and take the derivative of that expression up there with respect to u. Okay, so we're going to do each component individually. And so remember, this is going to give us a vector. Okay. And so for the x component, we have a minus a cosine b sine u. Okay. For the y component, we're going to have a cosine b u. And then for the z component does not have any u at all. And so we take the derivative with respect to u, we end up with 0. Okay, now let's take the derivative with respect to v. And so when we take the derivative with respect to v, we get minus a sine b cosine u, and minus a sine b sine u. And then for the y component, we have an a cosine u. Or a cosine v, I'm sorry. All right, so those two vectors there, and so these are two vectors, together they define the tangent plane, okay? But what's more important, the one that we're actually more interested in is the normal vector. And remember, to get the normal vector, we're going to take the cross product between these two quantities. For the normal vector equal to partial r partial u crossed with partial r partial b. Okay. So I'm not going to go through the math just because cross products are a little bit time consuming. And I want to make sure I at least get through surface integrals today, so you can start working on that for the homework. Okay. But the cross product for this, if you carry that through, is cosine v cosine u. Okay. And then cosine v sine u. And then sine. So what I'm going to say is that this, you should verify. Okay. So definitely, if you have time, definitely go through and it's good practice for the cross product as well. And so, if you have time, go ahead and verify that. So I gave you the two vectors, partial r partial u and partial r partial v. Just go ahead and verify that's the result there. Okay. Okay. Although one thing I did do is I divided everything by a, so I normalized it. So if you're doing the cross product and you're getting an a in there, the reason is because we divided. All right, so that's kind of the basic idea. So if you have a parameterized curve or a parameterized surface, computing the tangent plane and the normal vectors, it's just taking derivatives and taking cross products. So it is tedious, and so it's not the most fun thing in the world, but at least it's fairly systematic. Okay. All right, any questions on this example here? Okay. All right, so let's talk about surface integrals now. So now that we know how to compute tangent planes and more importantly normal vectors, we can start talking about surface. Okay. All right, so just like a line integral, in order to compute a surface integral, we need a vector field F. Right, so that's going to be the first thing that we need for a surface integral. The other thing that we need for a surface integral is some kind of surface S. And this surface S is a parameterized surface. So this surface S is going to be parameterized in terms of U and V. All right, and so the mathematical expression for the surface integral looks like the following. So we have a double integral surface S of the vector field F. Okay. And then we're going to take this vector field, we're going to parameterize it in terms of the surface coordinates. It's going to be F of R of U and V. Okay. Then we're going to take the dot product between the normal vector of the surface, U and V, okay. VU, V. All right. And so the process that we're going to go through for this surface integral is very similar to the line integral. So, we're going to start with a vector field F. We're going to represent F in terms of U and V. Okay? We're going to take the dot product between F and the normal vector, and then take its double integral. Okay, so what does this mean, right? And so, we've kind of spent a lot of time talking about kind of the details of the computation, but remember, the thing, because, essentially this is an engineering math class, I want to focus a lot more in terms of, what does it actually physically mean? Where are you going to see it in engineering? And what does it represent? So let's talk about its physical interpretation. So the surface integral, the thing about the surface integral is that it usually is meant to represent a flux or a amount of, how much a vector field passes through a surface. Okay. Right, so visually it looks like this. And so let's say that we have a surface. Okay. Okay. And so here I have a contact lens shaped surface. Okay. All right, so we'll call this a surface S. Okay. And this S is kind of existing in three-dimensional space. what can happen is that if you put this S inside a vector field, then some of the vector field's arrows, or a lot of the vector field's arrows, are going to pass through this surface. Right? And so I'm going to use red here. Red is going to represent the vector field F. Okay. And so what I've drawn here is that the vector field F, a lot of it is passing through the surface S. So where does this show up in engineering? And so where do you see this? And so first example I'm going to give you is, again, in fluid mechanics. You know, I can't help it. My background is in fluids. Okay. And so in fluid mechanics, you know, we use the surface integral to represent the mass flux. Okay? In fact, we also use it to represent the momentum flux. And so if you've taken fluid mechanics, and if you remember Reynolds transport theorem, right? Part of Reynolds transport theorem is, you know, how much mass, how much momentum, how much energy passes through a certain region. Okay? But I'm going to focus on the mass flux because that's, I think, the easiest to kind of understand. And so let's say that, you know, you're an engineer and you're designing the air conditioning system for a building. Okay. And so that's a very common, this is a very common fluid mechanics type of field, which is, you know, heating, ventilation, air conditioning, HVAC. Okay. And so oftentimes what you're interested in is, you know, say we have like one of the vents in this room, right? It's not on right now because it's freaking cold outside, but normally, you know, there's air conditioning coming through that vent, right? What you're interested in as an HVAC engineer is, you know, how much air, how much volume, or how much mass flux of air is going through that vent. And so you can represent that quantity, or you can compute that quantity with a surface integral. Right? And so let's say that, you know, you're running a CFD, you have a representation of the velocity field of the air that's circulating through a building. Right? And if you have the velocity field, you want to know how much air is passing through this particular vent. And so that's what you use the surface integral to represent. Okay. Another place you'll see this quite often is in heat transfer. And so heat transfer, one quantity that's mentioned a lot in heat transfer is this idea of the heat flux. Where the heat flux represents how much energy is passing through a particular surface at a given time, okay? And so same thing, so I'll use the same analogy. So let's say that we have the air conditioning on, or let's say we have the heater on, right? So if we have the heater on, you know, and we want to compute how much heat or how much energy is coming through that vent that's heating this room. Okay. So this idea of flux is used, you know, quite a lot in engineering. I'd say it's actually more common than the mining. Okay. But a lot of times you have, you know, anytime you have a fluid that's moving something, you're interested in seeing, you know, how much how much of that thing is being transported by the fluid, and you use the surface integrals to represent this. Okay, so let's do one more example before we end class today. So let's do an example of actually computing a line integral. Okay. Okay, so in this example, let's say we have a velocity field. And so let's say we have a vector field F. This is going to be equal to 3z squared 6, 6xz. Okay. And so what we want to do is we want to compute the flux of this vector field. Through the cylinder. It's not a cylinder, it's kind of like a cup kind of thing. Okay, through this surface. Y is equal to x squared, 0, oops. 0 less than or equal to x, 2, and 0 less than or equal to z. Okay. So what we have here is kind of I guess it's a cylinder. It's like an ellipsoidal cylinder. Right? So it's a cylinder where it's going to be wider in one direction than the other. Okay? And so what we want to do is we want to basically, since this problem is set to compute the flux, basically we're computing the surface integral of this vector field. All right, any questions on the problem setup here? Okay, all right, so let's go ahead and get started. So computing surface integrals, it's actually quite a long process. So there's quite a few things that you need to do. Right? And the number of steps that you do also kind of depends on what's given to you as a problem. In this problem, we kind of need to start from all the way from scratch. And I did this on purpose just so you can kind of see all the steps. So let's start with the first step. And so the first step is to parameterize our surface. And so our surface right now is given in terms of x, y, and z. So that's not going to work. It's remember, in order for us to perform surface integrals, we have to parameterize our surface in terms of two variables, right? I like to use u and v, but you can use whatever you want. You can use j and k, smiley face, frowny face, whatever variables that you want. Okay. But basically, we need to reduce the number of variables in this surface by 1. Okay, so how you do this? If you have a fairly standard shape, so if you have a cylinder or a sphere or a box, which is even better, you can use kind of one of the other expressions that we've had before. Here, we're actually given kind of a nice hint. We're given the hint here that y is equal to x squared in this expression. And so what I'm going to do is I'm going to set x of u and v. I'm going to set that equal to u. Okay. So I'm just going to kind of set this or define this. And so if x of u and v is equal to u, then y, which for our surface, y is equal to x squared, then we know that y of u and v is going to be just u squared. Okay. And so we basically are saying that, we have X, Y, and Z right now. So our surface is defined by X, Y, and Z, but we kind of need to flatten this. So we need to basically reduce the amount, but we do have one hint from the surface that Y is equal to X squared. And so if we said X is equal to U, then Y is just going to be equal to U squared. Right? Make sense? Okay. And so that all that leaves is just Z of U and V. The V of U and V, we haven't used the V variable yet, and so I'm just going to set Z of U and V is equal to V. So this one will also be the set. Okay. And so if we write this out, our R of U and V is equal to U squared. All right, so now that we parameterize our surface, our next step here is going to compute the tangent plane and the normal vector. And so for the tangent plane, we know that we're just going to take our parameterized surface and take the derivative with respect to U. And we're also going to take R and take its derivative with respect to V. So partial R, partial U, let's go ahead and compute this. So we have 1, 2U, 0. And then we have partial R, partial V. It's going to be 0, 0, and 1. Okay. And so our normal vector is going to be the cross product between these two. Okay. And so to take the cross product, this gives us minus 2U minus 1 and 0. Okay. Okay. All right, so now that we have the normal vector, let's go ahead and express our vector field F in terms of U and V. Okay. All right, so our vector field F, let me just go ahead and write it again here just to remind you, we have 3z squared, 6xz, okay? We're going to replace the x, y, and z here. Well, there's no y, so it's just x and z here with our parameterized curve. Okay? And so instead of 3z squared, from our parameterized curve, we know that z is equal to v. And so it's going to be 3v squared. 6 is just 6. And then 6xz is going to be 6uv. Okay. F. Perfect. Okay, so let's compute the integrand. And so our integrand, remember, is f dot n. Okay. So we're just going to take our two results here from our last two steps and take their dot product. We have 3v squared, 6uv, dot product with 2u minus 1 and 0. And so we take that dot product. What we get is 6uv squared minus 6 plus 0. So finally, we arrive at the last step, which is just to integrate. And so we're going to take the double integral. 6 uv squared minus 6 du dv. Okay. We need to set the bounds for this integration. So the bounds for this integration for u, remember u here represents x. If we go back to the problem, okay. We know x varies from 0 and 2. So we're going to integrate from 0 to 2. And for v, our v represents z, and for z varies from 0 to 3. Okay. Okay. So we have a fairly basic integral here, and so these are just polynomial terms. And so if you perform this integration, what we get is 72. Okay. So dot here, I performed double integral. So once you basically parameterize the surface and you computed the integrand, kind of the magic of the surface integral goes away, and it becomes just like a normal double integral. Okay? And so once you get it into that point, then you can just take a simple integral from there. Okay. All right. And so this 72 here represents the flux of that vector field through our surface. All right. Any final questions before we wrap it up for today? Okay. All right. So we'll come back on Thursday and we'll talk about divergence theory. Okay. All right. So thank you everyone for coming today. It's really wet. It's really raining outside. So please stay safe, especially if you're driving out there. Please be careful. I almost got into a couple accidents on the way here. So, I don't want anything, be careful out there. Remember your health, safety is most important. So take care of yourself. Thank you guys for coming today, and I will see you all on Thursday. Oh. Wow. Oh yes. Oh yeah. If you did pick up your exams, I brought them here today. I brought the cheat sheets back today too. So if you want to pick up your cheat sheet, yeah, just do that part. Really, any fun questions before I close the Zoom? Okay.